So far, we've been talking about all the data coming into the shader. We've been talking about the UI settings and the matrices, the input structs. And in this chapter, we're going to talk about the Vertex Shader and the Pixel Shader, which are the places where this incoming data gets used. If you haven't already, go ahead and load up Chapter 9 Shader.fx and also the equivalent max file. And let's get started. So first, let's focus on the Vertex Shader. Remember that the Vertex Shader is a function, so all the properties and syntax that we learned about in Chapter 6 apply here. With functions in mind, let's take a look at the first line of the shader. It starts off with v2f. What's that? Remember that when we create a function, we start by giving it a data type, the type of data that it's going to give back when we're done. So if the result of my function is going to be a float3, I start out by saying float3 and then I give it a name. In this case, instead of the function returning a data type, like float3, it's returning a struct. Remember that I named the output struct v2f. So I start out by saying v2f because it's the type of data that I'm going to end up with when the function's done. Then I give the function a name. I've simply named it v. Now the nice thing about returning a struct is that I can put a lot of information into the Vertex shader and then return it all at once. Next, I define all of the data that this Vertex shader will need to use. These are called parameters. The first parameter that I'm passing in is a to v in. What's this? Well, this is the input struct, and I'm naming it in. In is the name that I'll need to use to reference the data that's coming in from the vertex. And remember that I named my input struct a to v. So by passing in a to v, I'm actually putting in position, texture coordinates, tangent, binormal, and normal. I'm passing all of that information into my Vertex shader just by passing in one struct. Again, what's cool about using the input struct here is that I get all the data that it contains in one nice little package. My second parameter is the position of the light source. It comes in as a float4, and I'm using the term uniform here to tell the program that this is data that's coming from a source outside the shader. Now notice that the shader, just like any other function, is enclosed within these curly braces, opening one at the start and closing one at the end. Now we're going to talk about what each of the lines of the Vertex shader is doing. What I want to do is help you recognize what's happening here so that when you look at another Vertex shader, you'll be able to understand it. I'm not going to go into a lot of depth about the math that's happening. I just want to share enough information to help you get started. That way you can open up lots of shaders and read them and learn from them. Instead of teaching you all of the specifics of this one shader, I'm sharing with you the general principles that most all shaders use so that you'll be able to start learning the specifics on your own. Alright, let's get started. So in the first line here, I'm creating my output struct and giving it the name out. So remember my output struct is named v2f and I'm naming it out. So whenever I want to put something in that struct, I'll start out by saying out. And you'll notice that now for the rest of the shader, most of my lines start with out dot and then one of the components of the output structure because I'm filling in my output structure with all of the information that my Vertex shader is calculating. On the next three lines, I'm doing some matrix multiplication with the incoming normal, tangent, and binormal. I'll need the normal, binormal, and tangent in the pixel shader to do the normal mapping. I'm going to need these three vectors in world space. When they come in to the Vertex shader, they're in object space. So I multiply them by world inverse transpose. What that does is it transforms them from object space into world space. Notice that I'm bringing in the vectors from the input struct in.normal. This is the normal component here, and I've named my input struct in here. So if I say in.normal, I'm getting the normal that's coming in from the input struct. So I'm bringing in the vectors from the input struct, and I do the math, I'm multiplying them by the world inverse transpose matrix, and then I put the results into the output struct, out.worldNormal, out.worldTangent, and out.worldBinormal. So these three elements of the output struct, I'm filling in with the correct information. The next thing we need to do is create a light vector in world space. The light vector is a line between the light source and the vertex. We use the light vector to calculate the diffuse and specular lighting in the pixel shader. We create a vector by subtracting the world space vertex position from the world space light position. Now, our light position comes in world space already, but our vertex position comes in an object space. In order to do math with these elements, they all need to be in the same space, whether it be object space, camera space, world space, etc. In this case, I'm going to be using world space, so I have to convert my vertex position from object space to world space. And I do that by multiplying it by the world matrix. What that does is it takes the object space vertex position and puts it into world space. Then I set that equal to a new float 3 that I've created called world space position. So now that I've got my vertex in world space position, I subtract that position from the position of the light source, and that's what gives me my light vector. And like I said, I'm going to be using the light vector in the pixel shader to calculate the diffuse and specular lighting. Now on the next line, we've got texture coordinates, and I'm taking the incoming texture coordinates and just simply setting them equal to the outgoing texture coordinates. There's nothing special going on here. I'm basically just passing the texture coordinates through from the input struct to the output struct. So no extra math needed on that line. Next, I need to calculate the eye vector, or the line between the viewer's eye and the vertex. I'll use the eye vector in the pixel shader to calculate the specular lighting. So just like with the light vector, I need to subtract the world space vertex position from the world space eye position. Now I just happen to know that this view inverse matrix contains the world space eye position in its fourth row. So to access that data from the matrix, I say view inverse and then this 3 between the brackets. And what this 3 means is that I want the fourth row of the matrix. And the reason that I say 3 is because it starts out with 0. So if I wanted the first row, I would say 0. But in this case, I want the fourth row, so I say 3. So I'm taking the fourth row of the matrix, and I only want the first 3 float values of that row, so I'm doing .xyz. If I didn't do this, it would give me a float 4, and what I really want is a float 3, so I'm saying .xyz because I only want those first 3 components. So I subtract the world space position from the world space eye position, and that gives me my eye vector, which I'm passing out to the output struct. Finally, I calculate the vertex position in clip space and pass that out. This line is probably the most important thing that the Vertex shader does. We're multiplying the object space vertex position by the world view projection matrix. And what that does is it converts the object space position of the vertex into clip space, or to its position on the screen. And now here at the end I say return out to pass out the outgoing, the out structure, which I've filled in with all of my data. And that output struct gets passed along to the pixel shader. So there you have a quick overview of what my Vertex shader is doing. Some of this math might be really new to you, but like I said, what I wanted to do was just give you an overview so that you can recognize some of the things that are happening here. So when you look at other shaders, you can see that they're doing things that are pretty similar. Now let's move on to the pixel shader. We'll just scroll down a bit here. Like I said before, a fragment program is another name for pixel shader. Just like the Vertex shader, the pixel shader is a function. However, instead of passing out a struct, the pixel shader is just creating a color as its end result, the final color of the pixel that it's working on. So we start out by just saying float 4, because that's what we're going to return. That's what the function is going to give us at the end. And I've given my pixel shader the name F, just to keep it simple. Next, we define the parameters that are getting passed in. Notice that I'm passing in the output struct of the Vertex shader, v2f. But in this case, I'm giving it the name in because it's an incoming struct to the pixel shader. I'll use this name when I want to reference the incoming data. I'm also passing in the light color as a float 4. And again, the term uniform means that the light color is coming from an environment outside the shader. In this case, it's coming from 3ds Max. Finally, at the end of this line, we have a binding. You remember bindings from the structs at the top? This binding binds the pixel shader to the output color, which means whatever color this function gives at the end is going to be sent to the frame buffer as a color. This binding is important because it tells the computer that the result of the pixel shader is going as a color to the frame buffer. All right, so let's get started with the shader. In these first two lines here, I'm sampling my texture maps. So I'm setting up a new float 4 called color texture, and then I'm using this built-in function called text2d to sample my texture map. So I'm taking my texture coordinates in.textcoord.xy, so my u and v basically of my texture coordinates, and if I wanted to, instead of xy, I could type uv here and that would work as well. And I'm using those to sample my texture map. Now this item here represents my texture map. It's called a sampler. We're not going to talk about samplers specifically right now. We'll talk about that in an upcoming chapter. But what this line is doing is it's finding the color of my texture at our current location. Same thing applies for the normal. So here I'm using the text2d function again with my normal map sampler and my incoming texture coordinates. But in this case, I'm multiplying by 2 and subtracting 1. Why is that? Well, a color has an RGB value, and each of those elements, R, G, and B, can range anywhere from 0 to 1. But a vector also has 3 elements, X, Y, and Z, but the elements of a vector can range anywhere from -1 to 1. And so what I'm doing here is taking the color from my normal map, and this color represents a normal. But in order for it to become a normal, it has to be converted from the 0 to 1 range to the -1 to 1 range. And so what I do is I multiply by 2, and then I subtract 1. And what that does is it expands the range of my normal so that instead of going from 0 to 1, now it's going from -1 to 1. So what I end up with is a normal. All right, in the next three lines, we're bringing in our world space normal, tangent, and binormal. And basically all these three lines are doing is giving these three vectors nice workable names that we can use. And these are the vectors that I'll be using to convert the normal that I've sampled from my normal map from tangent space into world space. So, like I said, the problem with the normal vector that we got from our normal map is that it's in tangent space or UV coordinate space. And we're going to be doing our lighting calculations in world space. So I need to transform the tangent space normal map into world space. And I do that by multiplying the components of the normal with the world space normal, binormal, and tangent, then adding them together. So you can see here, I'm taking my world space normal and multiplying it by the z component of my normal map. I'm taking my world space binormal and multiplying it by the x component, my normal map. And I'm taking my world space tangent and multiplying it by the y component. Now you'll notice that I negated this here. Well, that's because some normal maps have the green channel going one way and some normal maps have the green channel going the other way. In this case, I have it going in the way that requires you to add a negative in this spot. So anyway, then I take the results and I add them all together to get n. And then on the next line, I'm using the built-in function normalize to normalize n. In order to do lighting math with my surface normal, my light vector and my eye vector, all three vectors need to be the same length. When I create a vector, it could be any length, but in order for the math to work right, the vectors all need to be the same length. When I use this function normalize to normalize the vector, it gives me a vector with a length of 1. The vector's still pointing in the same direction, or now it's the length of 1. And you'll notice that on these next two lines, I'm bringing in my eye vector and my light vector from the Vertex shader, and I'm also normalizing them. And so the result of that is now I have my normal vector, my eye vector, and my light vector, and they're all three the same length, which means they're ready for me to do the lighting math with them. Okay, so at this point I'm ready to start calculating my lighting. And the first part of the lighting that I'm going to calculate is the ambient light. And to do that, I'm going to take my ambient color that I pass in from the parameters. Go over here in Max, if I bring up the parameter editor, one of my parameters is ambient color. So I'm going to take that color and I'm going to multiply it by the color of my texture map. So that'll give me the color of the object when it's just lit by ambient light, when it's not being lit by any other lights. On the next two lines, I'm going to calculate my diffuse color and my specular color. And the way that I do that is I take the diffuse color from the material panel, this color here, and I multiply it by my texture. So that gives me my final diffuse color. And I'm going to do the same thing with my specular color. So I take the specular color, whoops, go over here. I'm going to take this specular color here. And in this case, I'm going to multiply it by the dot A of the color texture. And what that is, that's the alpha channel. So I'm multiplying my specular color by my alpha channel. And that means if I wanted to, I could go in and paint a specular mask in my alpha channel of the diffuse texture to control the brightness of my specular highlights in different locations on my model. Some people like to paint a whole independent specular texture, so they have control of the specular color as well. But in this case, all we're doing is using the alpha channel of the diffuse color. Finally, we bring it all together here in this last line. You'll notice that I'm calling a function here called blin2. This is the blin lighting function that does both the diffuse and specular lighting. I'm passing the function my normal, my light vector, and my eye vector. And remember that all three of these have been normalized, so they're the same length and ready to to do lighting on. I'm passing in my diffuse color, my specular color, and also my glossiness parameter. All of these are the values that I've calculated up to this point. And they were all calculated for the purpose of doing the lighting, which is happening right here in this line. Now, I'm not going to go into the specifics of how this function works at this point to calculate the lighting. In an upcoming chapter, I'll discuss diffuse lighting and explain the math behind it in depth. Anyway, so to finish up, we multiply the results of our lighting by the light color, and then we add the result to our ambient color that we calculated before. So here I'm creating this float for called C and setting it equal to the ambient. And now I'm adding the diffuse and specular lighting to the ambient. So I've got diffuse, specular, and ambient all together. And then right at the very end, I'm returning C as my final pixel shader output color. So there you have it, an overview of the workings of the Vertex and the Pixel Shader. We'll finish up our tour of the shader in the next chapter by talking about techniques, passes, and render states. Once we're done with our shader tour, we'll go back in and start using all the information we've learned so far to create some sample shaders.